prior standard deviation, because it is. So here's another one of these caterpillar plots of the ranks and their spread. This is an example just to show again that optimal is not only better, but is in some cases a lot better. This is the difference of the posterior mean from the optimal ranks, and then the triangles being the y's or the direct estimates. The x's are almost hidden in there because in this case things are quite Gaussian. Posterior means do very well. As you can see, the deltas are all over the place, showing that if you believe that what I've given you is optimal for at least squared error loss, you're getting a lot of discrepancy for the triangles. More importantly, and this is where you could accuse me of cheating, I have never run a simulation of a uniform zero correlation distribution on the interval 0, 1 with a random number generator that's been validated that has ever looked this good. I mean, this is almost like put me in jail for cheating, but this is the ranks based on the MLEs, least squares means really, versus ranks based on the z-score testing. And if you ever wanted to see a plot that says these two have nothing at all to do with each other, you probably couldn't do better than this. So it's trying to, I mean, I didn't try to make this happen, but it's sending the message that that choices matter in this case. And that in fact, the two extremes of use the MLEs and use the test, you really just, somehow this data set has conspired to give you incredible differences in this whole thing. I'm leaving these out, fortunately, because they're small. And go on to another, not another Bayesian formulation of the hierarchical model, but another goal that you might have in your analysis. And this is one that's a little more relevant, I think, not only for the health services application where CMS penalizes the poorly performing units, but for gene identification, SNP identification, and other things where you actually say, I don't really care so much how the ranks go for the things that are down there at low and in the middle, if high is the thing of interest. I'd like to do a really good job of selecting the top 1% of SNPs or 5% or 100 SNPs or whatever. And so take a different criterion, one that is not squared error loss, but says I'm going to keep score by counting up the number of or the probability that the true percentile for this SNP or this unit is below some threshold gamma when I estimate it to be above gamma. And this is indeed a Bayesian FDR. And I'm going to add to it, and I'll tell you why in a second, the other side, which is the probability that you went the other way, that the truth is above and the estimate is below. Because everybody's got to be someplace. There's a good joke about that, but I won't give it. Any misclassification above has to be coupled with a misclassification below because there are only a certain number of places to be. So the sum of this is actually like the FDR divided by this threshold gamma. And I like this normalization because it actually flattens the dependency on gamma, which we'll see in a few minutes. But if you wanted to, this has dividing by gamma has nothing at all to do with what you're going to use as your optimal estimate. It's just deciding where to keep score. So if the data were completely uninformative, in other words, the sampling variance were infinity for everything, this operating characteristic would give you a value of 1 always, no matter what gamma is. That's kind of the normalization. And of course, if they're fully informative, it would give value 0. So the idea here is going to be to come up with the P super est, or the pests that minimize this function. And it doesn't take much to see that the way you'll do it is to order these things in terms of their posterior probability of exceeding gamma. And that will be the optimal way to minimize this. So before I do the optimal thing, what I've done here is to take that computation of the posterior probability of exceeding a threshold, and in this case it's exceeding, excuse me, either the upper or lower 25%. You would never want to do that for genes, but just to make it easier to see what's going on here. This is the collection of posterior distribution, posterior probabilities of being in the top 25% of the dialysis providers. That's a bad place to be because it's SMRs. Similarly over here to be in the bottom. I'm ordering though now here by these p hats. They were not designed to optimize this criterion. They were generalized squared error loss, and that's why you get, these have all 3,459 on them. That's why you get these fat lines, because this ordering is not exactly monotone with these probabilities. We'll get to a plot in a minute that's much more boring in that it only has a line because you just do the right ordering. But this is to show that general purpose ones don't do too badly on this, but to show some other things. If there were no information in the data, then both of these curves would be flatlining at this green thing. It would just be, well, the probability is 25% because it's 25% up there. If you had fully informative information, being careful of what R does, it would be flatlining to there and jump up immediately to 1. The operating characteristic curve would say, no chance, no chance, no chance, bang. This one, these are in between, so it says there's some signal, but the main message here again is uncertainty, in that for the dialysis centers that are pretty much on the threshold of this upper 25%, that lowest one only has about a 40% chance of really being in the upper 25%. And you have to get way up here to the ranks that are up there, or the percentiles up there above 95 and so on, before you even get a 90% chance of truly being the ones that are up there. So this is another kind of uncertainty plot. If you do it with the, I'm going to quickly go to the plot and then I'll go back if I can find the plot. If you do the optimal ordering for this goal as opposed to the other goal, you're going to get thin lines because in fact these are now completely lined up. They're ordered by these. And for the moment, all I want you to do is doesn't matter which curve you look at, but you get the same kind of operating characteristic curve that if it were a perfect classifier would be 0 here and jump up to 1. If there are no information at all, in this case I'm doing top 80%, it would flatline at 0.2. So you can see there's some information, and we'll come back to these plots in a minute. Should have thrown one in there earlier, but I didn't. This is a easy computation to show that what you want to do is order the clinics or the units, whatever they may be, based on these posterior probabilities of exceeding this gamma thing. Early on in our research, we realized that, or at least we didn't realize, what we did was a naive computation of this, of running MCMC essentially forever, to get a good estimate of the posterior distribution of each of these clinics in this case, and then doing these computations. And it was endless because you have to, we had 3,459 of them. To get a fine-grained estimate of their probabilities, you need thousands and thousands and thousands of draws. Rongheng Lin, a graduate student of mine a few years ago, we came up with a nice theorem that says you don't actually have to do that. All you have to do is produce the pooled estimate of the distribution of all of these SMRs, or log SMRs, or whatever else you want it to be, by simply, in the MCMC world, taking all the draws you have from all of the clinics, throw them in one big hopper, order them, and let that be an overall pooled distribution that I'm calling G bar. If you're in a more mathematical statistics world where you don't have to do MCMC, you're just taking all of these posterior distributions and averaging them. And that a very trivial computation says you get exactly the same ranks, and there's a theorem that floats around here to say, if you want to find the probability of exceeding gamma up here, just find the gammath percentile of this pooled distribution, and this pooled distribution is for free, if you'd like, once you've either done the math or the MCMC. The threshold you should use here is just that percentile, and then just go take its single posterior distribution and compute this probability and order on that. And you get exactly the same answer. So this has a dramatic computational advantage, but it has an advantage even if it's not computational. This percentile is back in SMR land, or log SMR land, or whatever context you're in. So you actually get a number here that relates to the context and isn't just a rank or a percentile. So it helps map things in. This computation, not this computation, but this criterion is very similar to one that Sharon Lees Normand has used in health services work of probability of exceeding a threshold. And our only innovation, if you'd like, is to relate that threshold to a percentile of the rank distribution. So everything I showed you with those pictures was based on a Gaussian distribution for the log SMR. But the nice thing is, and one of these things that has really allowed Bayesian formalism to be quite objective for problems where you have a large number of units, is that you can become very much more empirical about the prior and not necessarily have to say it's Gaussian or it's anything. So this plot is saying we've done the Gaussian things in two different ways, but eventually this dotted curve is saying here's our best estimate of the prior distribution for those dialysis centers with a mean and a variance, and this is actually for the log SMR. But we also ran a smoothed non-parametric approach to it, saying all we're admitting to is that there is a prior, not in any way saying what it is, not giving it a name, and smoothing it. And you end up with this solid curve, and you could argue about whether we should smooth it a little bit more. The point is, the fact that it looks reasonably Gaussian in the center has nothing to do with our having made that assumption at all. It just happens to be that way. But we do end up with this little blip out here of a log SMR of about 0.5. Interestingly, these turn out to be the for-profit dialysis centers. I mean, not completely, but most of that little subpopulation is populated that way. The point being, everybody's subjective to some degree on deciding on the sampling distribution. Is it Poisson? Is it negative binomial or whatever? Frequentist Bayesians, we all have that. With these large data sets, large in the sense of number of units, so we get lots of draws from the presumed prior, we have the luxury of saying the only assumption we're going to make essentially is that there is a prior. And then let the data give virtually all details on it, and then use this shape, the solid curve shape, in our inferences and get a much more robust approach to things. I'm going to do just a couple of more things. I don't want you to look at necessarily to look, well, I don't want you to try to look at the details of this, but to say another nice advantage of the Bayesian formalism that allows you to do things that are at least more difficult to do as a frequentist is to say, I've got these true thetas, but I actually, in this case, we have 4 years of data. So we have the true SMRs or log SMRs for 1998, 1999, so on and so forth. Maybe we should build a model that includes both this cross-sectional combining that I've just done, but also the idea that the true SMR for a given unit for next year isn't a complete random draw from what it used to be, but is, in this case, an autoregressive model. So don't bother looking at the details, except for me to say this stuff says, let's build an autoregressive model longitudinally for these thetas, and still this general shrinkage model cross-sectionally for these thetas. Write the model in terms of the thetas, which we never get to see. We get to see the y's, and then let the technology take over to do what it needs to do things at the theta land when we only have the y world, and let the computer work hard to do that once you've formulated it. So